Right, so we're in the midst of chapter 16, right? There's one more section that we're going to talk about tomorrow. Today we're going to talk about interference, and then tomorrow we're going to talk about resonance. Okay, that's the last two sections in chapter 16 we're going to go over. Thursday we're going to start chapter 17, which is on sound, which is just another type of waves, right? And we're going to see a lot of comparison between just waves in general / waves on a string, and also sound waves and how those are related to each other. And then we're going to quantify a lot of different things about sound waves that are useful in real life when you want to figure out how loud something is, right? How, if you were twice the distance away, how loud would a particular sound be? And we've kind of already seen some of this in our analysis of waves in general. But at the end of class today, we're going to learn how waves interfere with each other. And this is going to be the section on interference of waves. And this is how there's a lot of interesting properties you can use to create this. One of the useful application of interference of waves are these things called noise canceling headphones. If anyone ever used one of those, there's actually a way for the headset to basically have a phase shift of 180 degrees of the wave that's being broadcasted, you're being heard, and then your headphone actually plays another sound that's exactly upside down from that wave, and therefore the waves actually cancel each other out. We're going to see this effect today. Okay, let's talk about let's go over what we already learned about waves, right? Waves can be written by this complicated equation that depends on both position and time. And they're just, complicated differential equation that we don't really solve, but it's interesting that it gives us various properties such as the speed of the wave, right? So the speed of the wave on a string can be calculated. And yesterday, we also figured out how much power, right, can be emanated from a wave by this long, crazy equation with 1/2 the density of the string, amplitude square, omega square times the speed. The main thing we want to take away is that the power, right, in a wave is actually proportional to the amplitude of the wave square, okay? Because you wouldn't think, well, if I make the wave twice as tall, right, it's twice as much power, but it's actually 4 times as much because it actually goes as the amplitude square as opposed to just the amplitude itself. Okay, so what we're going to learn today is how when mechanical waves get reflected or transmitted through a boundary, I'm going to look at this in a second here, what happens to them, and also what happens when you stack 2 different waves that are slightly shifted relative to each other. What happens when we stack 2 different waves together? This is known as interference of waves, right? Or also known as superposition of waves, because they're superimposing 2 things on top of each other. So whichever way you want to know the nomenclature, I'll leave you to decide which one makes more sense to you. And then we're going to calculate, what's the resultant wave when you have 2 sine waves that are superimposed on top of each other and therefore affect the net resultant wave, okay? So when we bounce a wave off a wall, I can actually probably demonstrate this on the string, but hopefully you guys can actually picture this, right? Where let's say I have a little pulse wave, right? And the pulse hits the wall. What happens is that when it hits a wall, it actually bounces back upside down, okay? So you can imagine that when a string hits this, the pull is being pulled up, but what happens is that since this is a fixed point, it cannot go up. It actually reflects that energy back downward, okay? So when a wave hits a fixed boundary, okay, what it does is that it turns the wave upside down, okay? So hopefully that's not too far a bridge, right? But if the other end is not fixed, let's say it's loose by this, kind of special ring, right? What happened is that instead of the energy being bounced to the downward, it just kind of transmits that. It's just kind of oscillate up and down. So this ring is allowing the string to go up, and therefore, when it have what's known as a free boundary, therefore it's not fixed, right, is actually going to bounce back without being upside down. Okay, this may kind of seem a little bit of abstract right now, but we're going to see how this is actually going to turn out when we have musical instrument, like the difference between a flute and a flute. I think that's the closed-ended instrument, and the clarinet, which is actually an open-ended instrument, and that makes a different sound because of that. Okay. You can also have partial reflection. This is probably more important for those of you going to be going on to study more physics when we do quantum mechanics. But you could have a case where the wave actually get partially reflected. Let's say you have a string that has a low density, so it's a thin string, but then you have a thicker string, like a thick rope or something like that. You tie the two together. What happens is that when you send a wave at this transition between the thin and the thick, part of the wave actually gets reflected, part of the wave gets transmitted. But we're not going to use that much, talk too much about that in this class because it gets into like kind of complicated calculation in order to actually predict something from that. Okay. Just to know that this actually also happens when you have this partial transmission. But the main focus on this section is going to be this idea of superposition and interference. Okay, so to me, those are the synonyms for the same word. Okay, let's see what happens when we stack two different waves together. Okay, the first one we're going to do is constructive interference. Okay, let's say you have wave number 1, which is this blue wave up here. Okay, and then wave number 2, which is this red wave. You can see that, right? If you line up the peaks of the waves, right? The peaks lines up with the peaks, the trough lines up with the trough, right? What happened is that when you put add those two waves together, let's say you have it's like an ocean wave where you have two waves that just kind of merge together into one. Okay. What happens then is that the amplitude of those waves just get added together. So let's write this as with the variables here. Let's call this y1, right? Depends on both x and time. This is y2, that depends on x and time. Okay, it's going to be called yr, where this is known as the resultant wave, which is both y1 and y2 added together. Okay, when you superimpose these waves together, right, the peaks line up with the peaks, therefore you make a bigger peak, right? The trough lines up with the trough, you make a bigger trough, right? The zero lines up with each other, you just get zero, right? So hopefully that makes sense, okay? When you add these numbers up together. Okay, so that may seem kind of boring, so like, it's just a wave that's twice as big, right? So from our analogy of what I said about noise canceling headphone, but what you can do is you can actually have a wave y1 and y2, but y2 here is 180 degrees out of phase relative to y1. Okay. Essentially, if you write the equation for y1 and y2, so let's say y1, right, is some amplitude times some sine of kx, is basically how we generally write a wave, omega t, right? And then y2 will be exactly the same, but have a pi, basically 180-degree shift to it, okay? This is where this phase shift thing we talked about when we introduced waves at first comes into being important, okay? So in this case, the blue, right? So the blue up here, we have at this position, we have the trough, but that lines up with the peak of the red wave. So when you add these two numbers together, one is a negative, the other one's positive, you get zero, right? If you move over here where you're looking at the peak of the blue wave, it lines up with the trough of the red wave. When you add those two numbers together, once again, you get zero. So the resultant wave is actually just zero, okay? And this is the idea of these things called noise canceling headphones, is that what the headphone is doing is that it's measuring the sound that's being you know, that's in the room, okay? And it'll play the exact same sound to you, but with this phase shift of 180 degrees, and therefore it cancels out the sound exactly. Okay, and that's the idea of noise canceling headphone. It doesn't work perfectly because sound is more complicated than just one single sine wave, right? But it works pretty well, and usually they tune it so it cancels out like lower frequency wave. So you hear like for example, this humming here, right? That's usually the sound you want to cancel out anyway, right? Because when you're talking to, when you still want to be able to hear people's voices and stuff like that. That's a higher frequency than this humming sound, right? So that's why you can actually cancel out certain frequencies of sound if you want. Okay. Any questions about this? How, just by shifting the red wave over by basically half a period, it makes this cancellation completely, which is known as destructive interference. Okay. Okay. All right. So now we dive into a little bit of algebra to figure all this stuff out, right? So actually, the way the book writes it, it puts the phase shift on Y1, but you can put the phase shift on either Y1 or Y2. It doesn't actually matter because it's just the difference between them that matters, right? Okay. So if we write the general equation for Y1, so it has some amplitude, it has some wave number, right? This wave number is 2 pi divided by the wavelength. And then this omega, right, is also 2 pi divided by the period, okay? And this phase shift thing, we're gonna put that in Y1, and then Y2 has no phase shift, right? So it's just it's as if, that phi for wave number 2 is 0, okay? When you add these two waves together, in other words, superimposing them together, right, you end up with this complicated trig function that has, a sine of some stuff, right, with the phase shift, and sine of the same stuff without that phase shift. You cannot just add these two things together, right? Because sine of 80 plus the sine of 50 is not the sine of 130, right? You can't just add those two numbers together, right? So what we need to do is do a little bit of trig identity. One of the trig identity is that when you add two sine functions together, it turns it into a product of sine and cosine, and then you add the stuff that's inside there, the u and the v, and you divide by 2. So there's a lot of stuff to keep track of in order to figure out what this means. Okay, so what I'm going to do here is I'm going to write this, right? Make this basically my u, right? This is kx minus omega t plus phi, okay? And v is going to be this piece here, right? Which is just kx minus omega t without the phase shift, okay? All right, so if we apply this trig identity, right? Whenever we see u in the equation, we're going to replace it with kx minus omega t with the phase shift, with the phi. Whenever we see a v in the equation, we replace it with just kx omega t with 0 as the phi, okay? There's always these factors of 2's around, so you have to keep track of that, okay? So what happened is that when you see this, right, that's actually, oops, when you see this yellow part, let me just kind of guide you to the right place. This yellow part goes with this guy, right? You see that? Okay. And then the green part, right, goes with this guy, right? I'm just replacing all the u's and the v's in this equation with what I define to be u's and v's, okay? It's just a substitution, okay? I do the same thing with the second term, okay? The only difference between the first term and the second term is that you have a plus and then you have a minus in the cosine, okay? Same thing here, right? All those 2's just kind of follows along. The neat thing is that, well, when you add these two together, right, you just get, well, kx plus kx, oops, right, just gives you 2 times kx, right? So I'm going to write one more line here so that it's a little bit more clear between these two, because the book, just kind of jumps to the next step and expect you to figure it out. write this like this. Okay. So when I add this term and this term together, right, you get 2 times kx. When I add negative omega t and negative omega t, I also get 2 times omega t, right? We're okay? Of course, this little phi is still around. Okay. All of that gets divided by 2. Okay. The cosine piece here, okay, right? Now, this is kx plus minus kx, right? That's going to be 0. Okay. So cosine, the first term is going to be 0. Okay. This is minus omega t minus omega t, right? So 2 minuses gives you a plus. So I also get a 0 for the omega part. So this used to be kx. This used to be the omega t piece. Okay. Then all that remains is actually just the phi divided by 2. You see that? Okay. So this equation actually simplifies to, well, you get twice the amplitude just because of this factor of 2 in front. Okay. Times some complicated stuff, right? Well, it's the same wave with half the phase shift, but then the cosine piece, right? It's just cosine of phi over 2. Okay. That's the neat thing, because the sine piece here, right, that depends on position and time. The cosine piece doesn't depend on anything. It's just well, once you know what the phase angle is, right? If I tell you the phase angle is 180 degrees, that's going to be just a number, right? Right? It doesn't depend on x or t anymore, right? Only the sine piece depends on x and t. That's the neat thing about it. Okay. So for example, right, if I tell you that the phase shift between the two is actually 0, right? The phi is actually 0, so we put in cosine of 0 here, right? Cosine of 0 is always going to be 1, right? So therefore, this piece just completely disappear, and you just get a wave that has twice the amplitude. Okay, and we had that example before up here, right? The completely constructive interference, right? The phase shift between them is 0. They are in phase with each other, so there's no phi of like pi or anything like that up here, right? When the peaks and the peaks and the trough line up with each other, you just get a resultant wave that has twice the amplitude, right? And this equation completely predicts that. I can go back down. Okay, right? So you get a wave that just has twice the amplitude. This is known as constructive interference. But unfortunately, I didn't give myself a lot of space here. Let's say the phase shift between the two waves is 180 degrees. You put in pi here, right? Cosine of pi over 2, cosine of 90 degrees is actually always 0. So you get a 0 at the answer here, because anything multiplied by 0 is 0, right? So in this case, you get complete destructive interference. And that's the second case here, where between these two waves, right, is shifted by a factor of just pi, or 180 degrees. That makes sense? And that's how you get little noise canceling headphones, by just shifting the wave that's incoming versus and playing a second wave that's actually the same wave, but shifted by 180 degrees. Okay. All right. And in reality, you actually get a little bit of both. Okay, a lot of times, so let's say you have some blue wave here and you add the red wave here. If you add these two waves together, you get like this funny little funny wave. Okay, you get a little bit of both usually. Okay, in reality, this not only applies to waves on a string, the ones we can see, right? It also applies to electromagnetic waves. Okay, this is kind of a cool image. You can actually probably see these on, well, when people used to have DVD, you can actually see this on a DVD, where it's actually constructive and destructive interference of different wavelengths of light. That's why you see this kind of like a rainbow color. These are known as interference pattern on a disc, or you can even see this through these things called diffraction grating. On a rainy day, if you go outside, you see a little oil slick on the ground, you can actually see these patterns also. Okay? And these are interference patterns because electromagnetic waves are waves, and therefore they can get constructive and destructive interference. Pushing this further, don't worry about this. If you're, you can stop listening if you don't want to. This is not going to be on the test or homework or anything like that. Not only do this happens to mechanical waves, sound waves, light waves, right, electromagnetic waves. If you take higher and higher physics, in quantum mechanics, actually all particles are waves. So an electron is a wave, a proton is a wave. So the stuff we're made of is actually all waves also. You can actually have things that happen that will interfere with each other because of the wave nature of everything in the universe. And you have these weird effects where even if, I don't want to try to describe this, this is a particular particle scattering off another. Even when that particular event, this particular process is not happening, the fact that it's possible, it actually interferes with the original process. It's like, you know, what's a good example of this? It's like, you know, you want to go to the grocery store, and then someone, you know, who lives in, you know, down the street from you does not want to go to the grocery store, and that actually slows you down because of the fact that someone else doesn't want to do it, which is like a completely weird thing that you know, I think in physics people are still trying to grapple with, and it's something that's very interesting, and the effect is very pronounced, and we can actually physically see them in experiments. Okay, so I have an example, and then we have a little worksheet that I think I should give to Ethan before. Any questions before I deal with the little example we have set up there? This is actually directly out of the textbook, so we can do more problems out of the textbook. Okay. So in this little example, we have two sinusoidal wave, meaning just a sine wave, right? That's traveling to some medium in the same direction. They have the same amplitude. So I'm going to start writing things down. Okay, so the amplitude is 3.00 centimeter, okay, or translated to 0.03 meters, okay? And it has a wavelength of 5.20 meter. What I'm going to do is I'm going to translate that directly to the wave number instead, which is just 2 pi over the wavelength, okay? That turns out to be 1.28, and this has this weird unit of 1 over meter on it. Okay, it has a period of 6.52 seconds. Then I'm going to also translate that to the omega, because the reason I'm translating it to these letters instead, right? Because those are the letters we actually use, those are the variables we actually use when we write the wave, right? The wave equation, right? So omega is also 2 pi over the period, right? And that turns out to be 0.9632, and this has units of radians per second, okay? Everything is in SI units, okay? One wave has a phase shift of phi, but the problem didn't tell you what it is, okay? Okay. What is the phase shift of the resulting wave? What is the phase shift if the resultant wave has an amplitude of 5 centimeters instead? Okay. So apparently, by having a phase shift, it changed the amplitude of the resultant wave somehow. Okay. Oh, 5 meter. Okay. So how does this happen? Okay, because we have two waves, right? Let's do my blue wave. This is the one I'm going to make wave 1 with the phase shift. This is the one with the shift. Wave 2 is going to be the one with no shift. Right? Let's do that in red. Y2, no shift. So I'm going to do wave 2 first, right? Because no shift is just a regular sine wave, right? Okay. With the shift, right? There's some shift here. Right? I'm going to start here. Even though I don't know what this number is, right? When you add these these waves together, right, you get a more more complicated wave. Okay. If they are completely constructive, right, then you get twice the amplitude. If they are completely destructive, the amplitude turns to 0, right? So the amplitude, right, is not twice as much. This is, twice the original amplitude should have been 6 centimeters, right? Right. So this is not complete constructive. It's not completely destructive. So it's somewhere between the two, right? So how do we figure out what that's going to be? So it's going to be some weird wave like this, okay? And this has some amplitude of 5 centimeters instead. Okay. Okay. This is where we're going to have to rely a little bit more on the mathematics of it, where, right, previously, go back up here, right, we were able to write the resultant wave with this equation up here, which is actually probably the important equation you want to copy down. Okay, it's twice the amplitude, and then the same argument inside, but then there's a bunch of phi over 2's inside the sine and the cosine function, right? So the resultant wave, right, is twice the amplitude normally, okay, times sine of kx minus omega t, but then there's this weird phi over 2 in here, and then cosine of phi over 2. Okay. Okay. So if phi was pi, right, then cosine of phi over 2 will be 0. Then you get complete destructive interference. But if phi is equal to 0, then cosine of 0 is still 0, right? So this twice the amplitude here only happens when phi is 0, right? But the resulting wave will have 0 amplitude if phi is equal to pi over 2. So the answer is somewhere between 0 and pi, right? Does that make sense? Right? Because we don't have complete constructive or destructive, right? Because the original amplitude is 3.00 centimeter, right? Therefore, twice the amplitude should have been 6.00 centimeter, right? Okay. We got 5 instead, right? So it's not 0, it's not 6, right? So somewhere between the two. Okay. So how do we solve for this? Okay. So what we're going to do is we're going to lump this 2 times a and this cosine of phi over 2 into one factor. Okay. So 2 times the amplitude, 2 times the original amplitude, cosine of phi over 2 should equal to the new amplitude, right? Which is the amplitude of the resultant wave. Okay. Okay. Right. So twice the original amplitude is 0.03 meter, right? Cosine of phi over 2 equal to the resultant wave's amplitude is 5 meters. Okay. Right. So now we have an equation to solve for phi, right? So this should be cosine of phi over 2 equal to 0.05 meter divided by 0.06. I just multiplied the 2 and the 3 together. I messed that up, right? Okay. And now, right, to solve this equation, I'm going to do inverse cosine of both sides, right? Inverse cosine of both sides. Okay. And that'll bring out the phi cosine 0.05 divided by 0.06. The units actually cancel out. I multiplied both sides by 2, and I should be able to get the answer. And if you did that, this answer will come out in radians, 1.17 radians, okay? Which is actually equal to, if you convert this to degrees, just so you can have a better picture of it, is about 67 degrees, okay? So this is kind of like the complexity of the problem we're going to be dealing with in this section, okay? Where we're interpreting, right? This is kind of like a modifier to the twice the amplitude that you would normally get, right? So this is kind of a factor that's, because this factor here, right? It doesn't depend on X, it doesn't depend on time. So basically it's kind of acts as an amplitude also. Okay. All right, so if we can pass out the worksheet. Any questions while Ethan's passing out the worksheet?